Now there are three types of metallurgy. One I have already discussed with you, rather two I have discussed with you. That is, I am telling you once again, the process of converting a metal oxide into its metallic form upon strong heating with a suitable reducing agent is known as pyrometallurgy. The process of converting a metallic oxide into its metallic form upon strong heating with a suitable reducing agent is known as pyrometallurgy. We can say that. Next is the process of reduction of the molten salt of a highly reactive metal is called electrometallurgy. The process of reduction of the molten salt of a highly reactive metal is called electrometallurgy. Next is the process of converting the impure metal present in an ore into a soluble complex by treating with a suitable reagent and then recovering the pure metal from the complex by treating with a more electropositive metal which is a stronger reducing agent is known as hydrometallurgy. I'll repeat it again. The process of converting the impure metal present in an ore, the process of converting the impure metal present in an ore into a soluble complex by treating with a suitable reagent and then recovering the pure metal from the complex by treating with a more electropositive metal which is a stronger reducing agent by treating with a more electropositive metal which is a stronger reducing agent is known as hydrometallurgy. So these are the three types of metallurgy, we can say that. Now coming to after the extraction of aluminium, iron, copper, we will come to the next one is extraction of zinc. We can say that the extraction of zinc. Now here you can see the entire process of how zinc is being extracted. We can say that in the refinery. So I will tell you that there are basic 4 steps. Same thing. The first is your concentration. So we generally extract zinc from zinc blend. We can say that ZnS. We extract zinc. It's from zinc blend. So first we'll go for concentration of the ore. Same thing. We'll go for concentration of the ore. That is a flotation process. And if iron oxide is also present, the ore is subjected to electromagnetic separation also, where iron oxide acts as an impurities here. Here iron oxide is an impurities. In case of hematite, iron oxide is not an impurities, but here in this case iron oxide is an impurities. We remove the iron oxide by electromagnetic separation. We can say that. Then after concentration of the ore, we go for roasting of the ore. The concentrated ore is roasted at about 1200 Kelvin in presence of excess of air, where zinc sulfide reacts with oxygen to form zinc oxide and sulfur dioxide is formed. Got it? Some part of the zinc sulfide also forms zinc sulfate, ZnSO4. ZnS plus O2 gives ZnSO4. Got it? ZnSO4 on further heating will give you zinc oxide and sulfur dioxide and oxygen gas is released. Achha. If calamine is being present as an ore, instead of zinc blend, if you take calamine as an ore, that is zinc carbonate, which upon heating in absence of air, that is ongoing calcination, it gives you zinc oxide and carbon dioxide. So by roasting and calcination, we have converted the ore into its oxide. We can say that. Next is reduction. Now several processes are used for the reduction of zinc oxide in a vertical retort process. You can see there in the diagram. That is a vertical retort process we have taken, where the powdered coke or coal is heated in a vertical retort along with the mixture, the roasted ore, we can say that. So the fuel gas and the air is made to burn, got it? And the heat produced in the retort is about 1600 Kelvin, where zinc oxide get reduced to zinc. Zinc, that is the reaction takes place is ZnO plus C gives zinc plus carbon monoxide. You can see there the entire process, you can see there it is being shown here. The zinc which is being formed gets vaporized, and the vapors of the zinc along with carbon monoxide are taken out from the exit near the retort. You can see is that is the off gas to washing tower, and the molten zinc we are getting in the refinery. We can say that. You can see there in the diagram. So the zinc which you are getting it there, the condensed zinc, the zinc which is condensed, it is known as a zinc spelter. Alright, that is a zinc spelter, which is an impure zinc, we can say that. Now this zinc is being taken, and it is the impure zinc is being taken, and it is undergone liquefaction process, or we can also go for distillation process also, we can say that, to extract the pure zinc. But better, I will suggest, we should always go for electrolytic refining to extract the, what you can say, not to extract, rather to get the pure zinc from the impure zinc, because electrolytic refining, the impurity the purity percentage is 99.99%, we can say that. But in liquefaction and distillation process, the purity is not so high as in case of electrolytic refining, so to say. Alright, so in this way we are extracting zinc from zinc blend, or from calamine also we can take it as an ore. Achha. Now next is the extraction of silver. We will see it is similar to that only. The name of the process is a McArthur Forest process. McArthur Forest process. Here we are taking, that is argentite, which is on a silver glance, Ag2S. We are taking as an ore. Got it? So the McArthur Forest process, it's also called as the cyanide process. This process is based on the fact that silver dissolves in a dilute solution of sodium cyanide to form a soluble complex called sodium argentocyanide. Alright, what I said, this process is based on the fact that silver dissolves in a dilute solution of sodium cyanide to form a soluble complex, that is sodium argentocyanide. Silver can be recovered from this complex by addition of scrap zinc. When we add scrap zinc acts as a reducing agent, which what you can say, converts silver, what you can say, ore to, what you can say, silver, we can say that. Now first what we'll do, as it is a sulfide ore, we'll go for the concentration of the ore, that is fourth flotation process. After that we'll treat with sodium cyanide. You may write down the reaction, that the concentrated ore is treated with dilute solution of sodium cyanide, that is Ag2S plus 4NaCN. Alright, the mixture is continuously agitated by current of air for several hours. We can say that the mixture is continuously agitated. The silver present in the ore passes into the solution in the form of soluble complex, that is sodium argentocyanide. That is what I said. Ag2S plus 4NaCN gives 2NaAgCN whole twice plus Na2S. 2NaAgCN whole twice is nothing but is your sodium dicyanoargentate, or we can say the common name is sodium argentocyanide. Now why we are blowing the air for several hours? Because the air blown oxidizes Na2S into Na2SO4. We are getting Na2S, na? Ag2S plus 4NaCN, what you will get? You will get 2NaAgCN whole twice and Na2S. Na2S is being oxidized into Na2SO4 by the blowing of air. Thus the reversibility of the reaction is checked, and the reaction proceeds in the forward direction. Alright, the reversibility is not taking place, because if Na2S is not being oxidized, it will again reverse the reaction. The reaction will again form, what you can say, Ag2S and NaCN it's going to form. So that is being checked by blowing air, because sodium sulfide is converted into sodium sulfate, we can say that. Done, this process is over. Now after that, the next step is precipitation of the silver. The solution obtained from the above step, which you are getting it, that is nothing but sodium argentocyanide, is treated with scrap zinc. It's treated with zinc. So 2NaAgCN whole twice plus Zn. 2NaAgCN whole twice plus Zn will give you Na2ZnCN whole 4. Sodium tetracyanozincate 2. Na2ZnCN whole 4. Sodium tetracyanozincate 2 plus 2Ag. the Ag is being precipitated, alright, as a dark amorphous mass. The precipitated silver is filtered, pressed, dried and fused with borax when a bright compact mass is obtained. Alright, the precipitated silver is filtered, dried, pressed and fused with borax when a bright compact mass of silver is obtained. Now this silver which you are getting it's an impure silver. We are going for electro-refining process to get the pure silver, so to say. Alright, the impure silver is made the anode and the pure silver is made the cathode, and we are taking sodium nitrate solution containing 1% nitric acid as an electrolyte. Alright, sodium that is a solution of silver nitrate, not sorry, sodium nitrate I am saying, silver nitrate solution containing 1% nitric acid as an electrolyte we are taking, or you can take sodium argentous cyanide solution as an electrolyte. Alright, in which that is silver, pure silver gets collected at the cathode, we can say that. So in this way we are extracting or we are collecting silver from the ores of silver, so to say. So in this way we are getting silver from its ore by MacArthur Forrest process. This is the process of liquefaction I am showing you here. That is impure metal is there, you can see, and this is sloping earth, impurities which is being left behind in the earth in the sloping, and the pure metal is collected at the bottom in the tank, we can say that. Now there are several processes of refining. I said you out of that electro-refining is the most economical and the easiest method of collecting of the what you can say the pure substance, the pure metal, we can say that. We have got liquefaction, the metals with low melting point like bismuth, tin, lead, etc. is purified by this method. Distillation, metals like having low boiling point is being purified by this method. Then cupellation, a cupel is a boat shaped dish made up of bone, ash or cement. That is a cupel, boat shaped dish, we can say that. The crude metal is taken in the cupel and a blast of air or oxygen is blown into it. Alright. The impurities are converted into volatile oxides which escape leaving behind pure metal. The impurities are converted into volatile oxide which escape leaving behind the pure metal. There is a crude silver metal contaminated with lead can be purified by this method, we can say that. Where lead is converted into litharge, PbO, which being volatile escapes leaving behind the pure silver. Alright, so this is known as cupellation. Then we can go for besmerization also, besmer in a besmer converter where impurities like arsenic, manganese, phosphorus, etc. Which is present in the pig iron can be removed by this method as a volatile impurities. Similarly, we can go for poling where poling is being done by the help of the poles of the green wood. Alright, where the metal oxide that is impurities to metal is being formed. Alright, by the help of the green wood we are taking it. That is, for example, if you take copper oxide, it reacts with methane which is present in the green wood. It converts into copper, water and carbon monoxide. So we are getting the pure copper by the help of the poling. But the best method I said you is nothing but is your electro-refining method, we can say that. Got it? Electro-refining method where the pure metal is taken as the cathode and the impure metal is taken as the anode, and the electrolyte is taken of that of the metal itself. Alright, and impurities which are being present in the anode in the impure metal is collected just below the anode as an anode mud or slime, and the pure metal ion is being collected at the cathode, we can say that. Clear? Then we have got zone refining where the impurities are more soluble in molten metal than in solid metal. We go for zone refining. Then we have also got vapor phase refining. In this the method, the impure metal is converted into volatile compound with suitable method leaving behind the impurities. Got it? Like example we can give the Van Arkel process, we can say that. In the Van Arkel method what we are doing is that it is used to purify crude titanium metal which is being heated with iodine to about 500 Kelvin to form unstable TiI4. Got it? It is being used to purify crude titanium metal. It is heated with iodine to about 500 Kelvin to form unstable TiI4 leaving behind the impurities. TiI4 that is titanium iodide is further heated to that is what you can say is that 1700 Kelvin over tungsten filament when it decomposes to give the pure titanium. Got it? That is titanium. We can say the equation in this way: Ti plus 2I2 in presence of 500 Kelvin will give you TiI4. TiI4 in presence of 1700 Kelvin will give you Ti, that is a pure metal, plus iodine is released. Similarly, zirconium also can be purified in the same way by employing iodine, like Zr plus 2I2 at 870 Kelvin will give you Zri4. Zri4 at 2075 Kelvin, still higher temperature, will give you Zr plus I2. There's a pure metal Zr, you are getting it. So zirconium and titanium can be used for purifying by Van Arkel process. We can say that Van Arkel method. VAN Van ARKEL Arkel. Next is the Mons process. It is used MOND apostrophe S. Mons process, it's being used for refining of the nickel metal, we can say that, in which the nickel, the impure metal, is being heated with carbon monoxide at 330 to 350 Kelvin to form nickel carbonyl, which is volatile, NiCO whole 4. Nickel carbonyl is further heated at 450 Kelvin to give you, that is, nickel and carbon monoxide. Nickel is the pure metal, we can say that, we are getting it. Nickel and carbon monoxide, we are getting it. Okay, the metal should form a volatile compound with this available reagent, and the volatile compound should be easily decomposed so that the metal in the pure form may be regenerated, we can say that. Now here you can see it is a column chromatography, the chromatographic method. It's a column chromatography which is being shown here. So by the help of column chromatography, what we do is that we remove the impurities present, got it, in the process by the help of column chromatography, that is chromatographic method. Now in this method, in the column chromatography, is based on the principle that the components of a mixtures are differently absorbed on an adsorbent. The components of a mixtures, various components of mixtures, are differently adsorbed on adsorbent. The method is especially suitable for the purification of those elements which are available only in minute quantities, and the impurities possess not much different chemical behavior as that of the element to be purified. Alright, in which the impurities does not possess much different chemical behavior as that of the element to be purified. Alright, in the column chromatographic technique, an adsorbent such as alumina, you can see is there in the figure, that is alumina is packed in a, that is glass column. The mixture to be separated or purified is applied on the top of the column, we can say that, on the top. The different components of the mixture get adsorbed in the column to different extents. Now a suitable solvent, which is known as eluent. Now the process is called as elution, E-L-U-T-I-O-N. What is elution? You can write it down: the process of separation of the different components of the mixture. Alright, the process of separation of the different components of the mixture from the adsorbent and the recovery with the help of suitable solvent. The process of separation of the different components of the mixture from the adsorbent and their recovery with the help of suitable solvent. Alright, that is called as elution, E-L-U-T-I-O-N, elution. Alright, so here I am saying you that is suitable, that is solvent, that is eluent, is made to pass through the column, because we are having two phases. One is the moving phase, another is the stationary phase. Alright, the weakly adsorbed components gets eluted first, followed by the more strongly adsorbed component, and so on. Thus all the components in this way pass through the column one by one and are collected in separate containers. We can say that. You can see the colored bands, we are getting it, and they are collected in separate containers. So this is known as column chromatography, we can say that. The solvent may be either the same which has been made, which had been used for dissolving the sample, or it may be different, we can say that. Alright, the solvent may be the same or it may be different. As the solvent moves down the column, the different components are being, what you can say, present in the chromatogram, begin to separate, and they form well defined colored bands, as you can see it there. If the sample under investigation is a colored one. Alright, if the sample under investigation is a colored one, then it forms different colored bands. In case of colorless sample, these bands are not formed. Alright, that you must remember. Some suitable physical and chemical methods are used to locate these bands which are formed at different places in the column. Alright, so it may be noted that the component which is least absorbed in the column gets most readily dissolved by the solvent, that is the eluent, and migrates furthest down the column. We can say that in this manner the different component formed bands at different places in the column. The formation of bands is called as the development of the chromatogram. We can say that. Alright, the development of the chromatogram. So in this way, by the help of the column chromatography, we also it is being used to employed on small scale for the purification of certain metals we can say that, and it is based upon the principle which I've already said you. All right, so this is all about your extraction of the different metals, so to say. How do we extract the different metals? All right, what are the ways of extraction of the different metals, and what are also the different methods we have discussed here, and the different definitions we have discussed here. All right, so this is all about in this particular chapter.